Good day, chemistry students. So, I'm going to give you a real quick rundown today on some concentration units, and we'll talk a little bit more about with one particular example. So let's talk about concentration of solutions, and let's first introduce a few terms that you may already be familiar with. So here are three that are relatively straightforward. We have percent by mass. We have the mass of a solute, dissolved smaller amount of substance over the mass of solution. If we have two liquids, or we could have volume of solute, volume over solution, for percent by volume. Or maybe we want to take percent mass volume, or take the mass of the solute over the total volume of the solution. A good example we might start with is looking at our blue Powerade here, right, that I borrowed from my pantry. And if I look closely at the nutrition facts, I can see that one bottle is listed as having, see if I can find that, zoom in a little bit, 60 milligrams of potassium. And if we look and we trust the manufacturer label, the volume is 591 milliliters. So let's use this example first, and we'll write this up here. So if I'm using a mass volume percent, I could write this as 660 milligrams of potassium, K, over 591 milliliters total volume, and I could calculate. Or I could express this by multiplying by 1,000 in both cases to convert from to grams and liters. And notice I'll end up with the same general calculation. I punch this in my calculator. I take 60 divided by 591. I get 0.1015. So I'm going to say that that's equal to 0.1015. But this is a percent, so I have to multiply it by 100. That's right, times 100, or over here, right, times 100, right? So if I do times 100, right, so times 100 in terms of percent, I get that this is 10.15%. Now I'm not worried about sig figs right now. Potassium in a mass volume percent. That sounds reasonably large. It does not. Okay, so let's try that again. Let's double check here. So if I take that, I take 60.06 divided by 0.591 times 100. Yeah, I get 10.5. So that's pretty good percentage in a mass volume percent. That tells us a certain amount of information that can be useful. Mass percent would be useful, etc. Okay? So let's look at some more. So we don't always want to report things in percent per 100, but sometimes we want per parts per thousand, parts per million, or parts per billion. So if we're talking about small quantities, right? So this again comes back to very much analogous to percent, only it's not, instead of it being per 100, it's per thousand, million, billion, or we could even go to trillion, right? And so this is set up very similarly. So I've refreshed the board because I want to move to something a little different. We've talked briefly about concentration in terms of molarity. So we might recall, if we look at the board in a second, I'll write up molarity equals number of moles of the solute per liter of solution. So notice here, our volume in the denominator in liters, our moles, not grams, of solute in the numerator. Okay, so moles per liter for molarity. Remember, the volume is the volume of the whole solution. Okay, this is not per anything else, so we don't need to multiply by anything here. This is our molarity. So if we use our example of potassium in our Powerade here, we've got to first convert from milligrams, 60 milligrams, 2 grams or 0.06 grams, and then convert that to moles. So let's do that on the board. So now I've expressed this. I've written my 60 milligrams. I could cross out milligrams because I've got 1 gram is 1,000 milligrams, metric conversion. And I multiply by 1 mole over 39.1 grams, which is the molar mass of potassium. And then I get that I've got 0.00153 moles of potassium per bottle, right? Good electrolyte ion that's needed. All right, and if we take our volume of 591 milliliters, let's write 591 milliliters. Remember, we want this in liters, so 1 liter, 1,000 milliliters. So we get 0.591 liters, right? And so now if we take this and we do this mathematical calculation, we find that the molarity of potassium in our Powerade potassium ion is, and we could write this sometimes, we'll write it, this is potassium ion, not a metal, right? In square brackets, which is sort of a way of shorthanding for molarity of our potassium ion, right, is now we find equal to be 0.0026. I'm going to go ahead and go back to kind of more appropriate scientific notation, moles per liter, right, or big M. And if we write this in scientific notation, we've got 2.6 times 10 to the minus 3 molar, right? And so if there are 2.6 times 10 to the minus 3, right, molar, we could also alternatively write this as 2.6 millimolar, because we know there are 1,000 millimoles per mole. So this is how many millimoles per liter, 2.6 millimoles per liter in the solution. This is, small but not insignificant. So this is our molarity of potassium here in our energy drink. Now, there are a couple other forms of concentration that we want to look at and introduce here. One of them is called molality. So we're going to change the R to an L. And molality, instead of knowing the volume of the solution, we need to know the mass of the solvent. That's a little different. So here we have our molality, moles of solute per mass of solvent in kilograms. Notice that's very different than a molarity. This is covered in Chapter 11, so if we're going to fast forward to Chapter 11 in OpenStax to look at that OpenStax chemistry. Now, if I wanted to do this measurement, I need some way of knowing the mass. And for our energy drink, unfortunately, we don't have an accurate reading of the mass, especially of water. Right? We could get the mass of the solution. We could try to subtract the mass of the electrolytes, but we won't truly know the mass of the solvent there. So it's kind of hard to get the molality here. We could try to use a measuring device and measure, right? But again, in this case, unlike in the lab, it's kind of difficult to do this. We could try to make a prediction, but we're left with that. So we need the mass of the solvent and the moles of solute. There are ways to do experiments with this, and undoubtedly if you take enough chemistry, you will. Now, one more example where we take moles of solute, right, and we've seen molarity and molality. Well, one other way we can do it is look at the mole fraction. And a mole fraction is simply that. It's a fraction of the moles of solute over the total number of moles of everything in the solution. Let's write that out as an equation. So here we have an equation, mole fraction equal moles of solute over total moles of solution. We could write this differently. Let's think about a solution, maybe like our Powerade, but maybe a little simpler, where we have like 3 things in the solution. We have solute A, solute B, and solvent. We'll call that S, just for now, okay? So if we consider that, then there's a certain number of moles of A, moles of B, moles of S. A plus moles B equals total plus moles of S equal total number of moles. And so that could go right here in our mole fraction. And if we want to know the mole fraction of A, we put moles of A over total number of moles of solution. The mole fraction, by definition, has to be between 0 and 1. Take that to heart. A mole fraction is a ratio of moles of solute. If it was 0, that means we have 0 of that solute, right? And it's kind of meaningless. And if the mole fraction equals 1, we have a pure substance, right? We don't have a solution. We don't have a mixture. So for a mole fraction of any solution, the number of moles of solute, if it's very small, ratio to the total number of moles, it's a very dilute solution. We have very little of that solute. If it's very large, closer to 1, we have a very concentrated solution, right? We have a lot of that solute, right? Effectively, we're talking about the solvent, if it's very large, mole fraction. So I would encourage you to look at these, read through these concepts. We'll cover a little bit more in class next week, and have a great day.